Hey everyone, welcome back to Math 11. So in this video we're going to be looking at scale diagrams and I'm going to mention scale factor. So far we looked at how we can use rates to solve questions. Now let's talk about cases where maybe you have to scale something up or scale something down. Let's say you may be renovating your house or something like that, or maybe you're a contractor. So in this case, in this example, we have a two-dimensional scale diagram that requires a reduction. So the question says, a builder plans to construct a house on the rectangular lot as shown in this sketch. Draw a scale diagram of the lot house using the scale 1 meter to 500 meters. All right, so let's first look at our diagram. So it looks like we have the lot, which is 40 meters by 50 meters. And then we have the dimensions of the house, which is 2 meters away from the, I guess maybe there's a fence or something. And then 4.5 meters down here, and then the actual length of the house is 12 meters and the width is 9 meters. So let's label each of these dimensions with letters, so we can just use letters to reference. So this distance, let's call this distance A, 2 meters. Let's call this distance B, distance C, call this D, E, and distance F. So now we can reference back to our diagram. Now, how do you use this scale? It's 1 meter to 500 meters. So if we're looking at our conversion of 2 meters here for part A or distance A, we're going to use our scale 1 over 500 because 1 to 500 means the same as 1 over 500. So that's going to be the first thing I'm going to write. I'm going to write the scale. So I'm going to say 1 meter over 500 meters. Now notice here that the units actually reduce away, they disappear, because a scale factor or the conversion factor is unitless, it's just a ratio. So in this case the ratio is 1 to 500. So even though you can include units to keep track what kind of units you're using, in this case we're using meters, but in reality it's just a number without any units because the units just go away. So let's convert this 2 meters using this conversion of 1 over 500. So we're going to multiply this by 2. Now this is 2 meters, right? So even though these units are gone, we still have the units of the actual dimension of 2 meters. So we're going to end up with a scaled down version of this. So, which we can then draw on a piece of paper, right? So these are the measurements that were taken, let's say, either from the actual house or he sketched it down. Like in this case, it says he's planning to build this. So we have to sketch it out. So 1 over 500 times 2 is going to be 0.004 meters. Now we want this in units that we can easily sketch, right? So we want to convert it to either millimeters or centimeters. So in this case, it's probably easiest to convert to centimeters because that's the easiest kind of unit to work with. Millimeters are maybe too small. So 1 meter has 100 centimeters. Okay? Which means if you want to convert meters to centimeters, you had to divide by 100. Or you can just move the decimal place 2 points to the right. So in this case, if you look, we have our decimal place right here. So if you move this 2 places to the right, you're going to end up with 0.4 centimeters. So that would be our value in centimeters. So this is going to equal 0.4 centimeters. Okay, so let's do the next one, which is B. So for B, we have, again, the same 1 over 500 times 12. This is going to equal to 0.024 meters. Now we're going to convert this using the fact that there's 100 centimeters in a meter. And we're going to move the decimal place 2 spots to the right, so it's going to leave us with 2.4 centimeters. Now you can do this as a separate calculation, but you probably know enough about conversion by now in grade 11 that you don't need to show every single step here. So Let's do the same thing for the remaining values. So part C is 9 meters. So we're going to do 1/500 times 9 meters. This is going to leave us with 0.018 meters, which again, I'm going to move the decimal to the right 2 spots. So we're going to be left with 1.8 centimeter. For D, we have 4.5. So again, 1/500 times 4.5. This equals to 0.009 meters. And again, move the decimal spot 1, 2, so you get 0.9 centimeters. And we have a couple more. We have E and F. So E is 40 meters and F is 15. So for E, 1/500 times E, which is 40. This is going to be 0.08. And we get 8 centimeters here. And the last one is 15 for F. So again, 1/500 times 15 meters, which equals to 0.03, which again, if you move the decimal 2 spots to the right, you end up with 3.0 centimeters. So there you go. There is your converted values to units that you can actually now use and sketch at the bottom of your page here. Now, I don't have a ruler to compare, but you would basically sketch it out like so, using the actual values. I mean, it's going to look, proportion is going to look the same as the sketch they have on the top of the page, but you want to use the actual centimeters that you just figured out the values for. So all the dimensions using centimeters, and of course you're going to end up with proportionally the same looking diagram, but you want to measure it in centimeters now. So this would be, here you'd have your 0.4. Right now this is going to be centimeters. This distance here would be, let me just write it here, 2.4 centimeters, right? So all the values that we just calculated here, this is going to be 1.8 centimeters. F, we found it to be 3.0 centimeters. This is going to be 8.0 centimeters, the length. And what else we have? This distance we found to be, this was D, which is now 0.9. So this is 0.9 centimeters. So you would actually sketch it exactly to scale using a ruler and using the centimeter values. So you reduced it by 500 factor. So, so the definition that we probably should introduce here is the scale factor. So let me write it down here. So scale factor. And again, you can read this in your textbook as well. It's a number that's created from the ratio of any two similar shapes or objects written as a fraction, decimal, or percent. So again, number created from the ratio of any two similar sides or shapes. So in this case, we're comparing the sides of whatever either the house or the side of the whole lot. Maybe there's a fence around it. So similar shapes or objects written as a fraction. So again, a lot of the stuff you probably remember from like grade 8 math. Fraction, decimal, or percent. Or a ratio too. I should add that in. Or a ratio, that's how it's written here. So if you remember, this is your ratio notation. When you have something like this, 1 to 500, this is called ratio notation, which is equivalent to 1/500 in fraction form. So this is fraction. And then when you actually divide 1 by 500, so let's say I divide 1 divided by 500, this is going to be equal to 0.002, which is decimal form, right? So I have ratio notation, we have fraction notation, we have decimal form, and if you multiply your decimal times 100, you're going to get your 0.2%, which is percent form. So all those are forms that we can state the relationship between two sizes, two similar shapes, or two similar objects. All right, so let's take a look at one more example, and we're going to be using this case. On the next page, we have to find the scale factor. So in this case, we have a diameter of the animal cell that's shown on the right here, represented by the scale diagram is 0.25 millimeters. What scale factor was used to draw this scale diagram? So we have some animal cell here. We have the diameter of 3.5 centimeters. So that's the diagram. It says the actual length is 0.25 millimeters, so 1/4 of a millimeter. So that's the actual dimension of the actual cell. So the scale factor, to define scale factor as a ratio, so scale factor, now I think the textbook uses just one letter for this, but you can use two letters if you want. You can say SF for scale factor or just SF. This is going to equal to the diagram measurement or photo, whatever you have. In this case, we have a diagram. So in this case, it's going to be diagram over the actual measurement. Now, the words that I use here might be a little different depending on the question. So the diagram measurement is either could be photograph, for example, as well, if the question talks about photographs. The actual measurement is the real life measurement. So in this case, the real life measurement of the cell is 0.25 millimeters. So that's what we're trying to find. We're trying to find this ratio, the scale factor. Now, again, there's a couple of ways you can do this. But the one thing that you have to be really careful with are the units, because if you look, we have the actual dimension given in millimeters and the diagram is given in centimeters. So before you find the scale factor, you have to have the same units, otherwise you will get the wrong answer. So you have two options. You can either convert millimeters to centimeters for the actual measurement, or you can convert centimeters to millimeters for the diagram measurement. Doesn't matter which one you convert as long as you have the same units. So in this case, what I've done is I converted the 3.5 centimeters to millimeters. Why? Because I know there's 10 millimeters per centimeter, so all I have to do is just move the decimal, or you can go through the steps of converting, which is going to be millimeters, centimeters. So I want centimeters to cancel out, so centimeters go on the bottom. I know that 1 centimeter contains 10 millimeters, which means that you just gotta multiply by 10, or move the decimal to the right by 1 decimal place. So you're gonna end up with 35 millimeters. So that's gonna be your diagram measurement, right? So this is your diagram measurement. So once you have your values for your dimensions in the same unit, what you want to do is then take your ratio, your scale factor. Now your textbook actually uses the letter K for the scale factor. So you're going to take your scale factor, and you can use the letter K if you want, or K. The diagram measurement is going to go on the top. So diagram is going to be 35 millimeters. Okay. The actual measurement is 0.25 millimeters. And if you divide this, this is already a ratio. You can leave it like this, and this would be okay, but we want to have a ratio that's just something without any decimals in it. We don't want to have 0.25. So what you want to do then is to multiply by some number, top and bottom, just like you've done, in grade 8 or grade 9, and to get it equal to some round number and then simplify it. So what we can do here, for example, to get rid of this decimal, there's 2 decimals, right? So in order to get rid of the 2 decimals, we need to multiply by 100. So you're going to multiply the bottom by 100. Now, if you multiply the bottom, you have to do the same thing to the top. So I'm going to multiply the top by 100 as well. So now I'm going to have an equivalent fraction, but the numbers are going to be bigger, of course. We're going to end up with 3,500 on the top and 25 on the bottom. Now here you can use your calculator for this if you want to simplify it. Again, you can just enter 3,500 divided by 25, and usually the calculator will simplify it for you, which is going to be 140. But to keep it as a ratio, we also need to know what the proportion is. So it's 140 to 1. So that's going to be our scale factor, 140 to 1. So the question was, what scale factor was used to draw this diagram? Well, it was the 140 to 1 ratio. So there you go. That's an example how you can find the scale factor from a diagram. If you have any more questions, make sure and post them in comments on Teams as a reply. And for homework, again, watching videos is not enough, so make sure you do the homework questions. So this is section 8.3. So read pages 474 to 479 and do questions 1, 2, 4, 11, and 17.